So I'm going to be doing a talk about cryptocurrencies, how to use them, and also a bit of an in-depth view into how they actually work. Because I think it's good to understand how things work before you actually want to use something, especially when it comes to money. So I'm Cyrus Massey-Cook. I've just finished my A-levels. In my free time, I do Java bytecode obfuscation. But I also do some cryptocurrencies. I'm not going to cover investment advice just because obviously that's a hot topic and I don't want to sort of tell you something and then you make decisions off that you regret. So when I say sort of blockchains, this is what you might think of, sort of these images that you often see when it's used as a buzzword. That's obviously not what a blockchain is. A blockchain is sort of a linked list of blocks which can just contain arbitrary data, and each block has a hash of the previous block. So the idea is that you couldn't alter a block in the blockchain without then having to recalculate the hash of every single block along the blockchain, which should be quite computationally expensive. And each block normally also has a limit on its size. So Bitcoin has a sort of 2 to 4 megabyte limit on the amount of data that can be stored in each block. And with technologies such as Bitcoin, the blockchain is normally distributed. So with Bitcoin, every single node, which is sort of a computer running Bitcoin, has a copy of the entire blockchain on their computer. And that way they can verify the hashes themselves, and they can look through the blockchain and find any data in the blockchain. And they know that it's secure because all of the hashes match up. So nodes, so as I said, nodes are sort of a computer that's running the blockchain or the cryptocurrency software. They normally have sort of a local wallet, so they keep track of a public and private key that can hold coins, and they can create, sign, and send transactions on the blockchain. So that involves sending transactions to other nodes, who will then distribute it to further nodes, and they will all add it to their local blockchains. They can also download blocks from other nodes in order to keep the local blockchain up to date, and they can validate blocks because they have the software, which includes the algorithm that will enable them to validate that a blockchain doesn't have incorrect data, isn't trying to sort of print money invalidly. And they can also mine new blocks. I'll go into mining later. So Bitcoin was developed by Satoshi Nakamoto, which is an alias. It probably isn't a real person, but it's the alias of whoever created it, and they developed it in C++ originally. Their original implementation of Bitcoin has been forked a couple of times, and it's the major implementation is currently called Bitcoin Core, which is still in C++, and it inherits some of the code from the original Bitcoin software, and it's open source under the MIT license. And it's publicly available. The source is all publicly available, obviously, and anybody can submit contributions that may or may not be accepted. And Bitcoin is often thought of as the first cryptocurrency. It wasn't really. It was the first cryptocurrency that solved double spending, though, because originally it would have, in a lot of original cryptocurrencies, it was possible to send money to somebody and then use that same money to send to somebody else, called a double spend, which is invalid. So Bitcoin solved that with the use of the blockchain, because through looking through the previous blocks, you can verify that that money has not been spent before. So nodes on the blockchain establish peer-to-peer connections with each other, sort of like a torrent, and they pass transactions and blocks between each other. The way that a node will always know which blockchain to use, because another node could send to it a new blockchain and say this is the real blockchain. And the way you know that a blockchain is the legitimate blockchain is if it is the longest blockchain you can find. Because to add new blocks to the blockchain, you have to calculate hashes, which is expensive. So as long as you have the longest blockchain, you know that's the one that was required the most computer power to generate. And that way, it's unlikely that it is malicious, because a malicious attacker would have to gain huge amounts of computing power in order to generate a blockchain longer than the current blockchain. And nodes attempt to create blocks on the blockchain by brute forcing hashes, which is called proof of work. And if it does successfully create a block, then it will send that to other nodes. And I'll go a bit more in depth onto that. That's called mining. And transactions can be independently cryptographically verified. So if I send you a transaction, it is signed with my address, which is obviously a public and private key. And you can verify that the signing is correct. And you can also, if you have a copy of the blockchain, you can verify that I do in fact have the money that I spend in the transaction. And the rules of the network are decided by whoever has the majority computing power, because as I said, the longest block is accepted. So if you can create a longer block following different rules, then you can essentially change the way Bitcoin works. And I've got an example here. If you wanted to double the mining rewards, because when you mine Bitcoin, you get a reward to incentivize people to keep the network alive. If you do want to change the mining rewards, you could fork Bitcoin. You could fork the software and add in to allow double rewards. Nodes in favor of the double rewards would include any blocks that contain the invalid or now valid reward and add it to their blockchain. However, nodes that don't want miners to get a double reward would simply not include it in their blockchain, and which, if the majority of nodes did include it in their local blockchain, eventually they would be able to build a longer blockchain than the nodes that did not include it, which would essentially make it the sort of the majority blockchain. And two blockchains can exist. You can fork a cryptocurrency and have two separate blockchains with different rules and different amounts on them, and that exists. There are alternative Bitcoins. So it's just about which one is known as the Bitcoin and which one's known as sort of a fork. So Bitcoin addresses are sort of asymmetric key pairs. You have a public key and a private key. The address isn't actually the public key, but it's a hash of the public key. It's SHA-256 and RIPE-MD 160. And that's also interesting because the fact that the public key is hashed makes it resistant to quantum attacks. So that's quite good, actually. And that just allows you to sort of represent a sort of 256-bit public key in quite a short address that you can send to people easily. And if you're interested in Bitcoin addresses, there's a tool here. It's just a GitHub gist, which you can use on the command line to generate yourself a public and private key pair and an address, so you can understand how it actually works. So the blockchain is a list of transactions. As I said, each block on the blockchain contains a hash of the previous block and a hash of all the data inside the current block. It also includes the timestamp of the block. The timestamp, because obviously there's discrepancies between different computers on timestamps, because clocks can get inaccurate or they can lose power. You find the timestamp by querying other nodes running, and you find the average of all of their timestamps, and you don't deviate by more than 70 minutes from your local time to prevent sort of attacks where you could create tons of Bitcoin nodes all reporting incorrect times. So it's a nice solution that allows you to find a timestamp that the network agrees upon that's reasonable. And transactions which have the timestamp off by more than 2 hours will be rejected. The target is a 256-bit number that is the amount of difficulty that the network currently has. So the hash of the block must be lower than the target. A SHA-256-bit hash is normally represented as sort of a string of characters, but in reality, it is just a number. It's a 256-bit number that you represent as hex. So when you calculate the hash of the block, it must be lower than the target. So if the target is really high, then that allows a lot of leeway in that the block could be any data and it would be under the target, and you could just instantly submit it to the network and it would work. If the target is really low, then that would require constantly changing the contents of the block until you could find one where the hash is underneath the target, and that would be quite expensive. So that's how you make it difficult for nodes to mine. And then you have the nonce. It's just a 32-bit number which you can just continuously change in order to affect the hash value. So you could just go through every sort of possible 32-bit number and try what the new hash of the block is until it's underneath the target. And then you have the list of transactions. Transaction is it's a bit more complicated than you'd normally think. It's a list of inputs to the transaction, which is basically if somebody else sends you money in a previous transaction, you can use that transaction as an input into a new transaction, and you can have multiple of those in order to get enough money to cover the amount that you want to spend in the outputs, which is another list of actually scripts, but I'll go into scripts later because they're a bit complicated. And all the outputs of the transaction are represented in satoshis, which is the smallest possible unit of a Bitcoin. So when you can buy a Bitcoin, but you don't have to buy a single Bitcoin. You can buy sort of 0.5 Bitcoin, and Bitcoin actually allows up to 8 decimal places of accuracy. So a satoshi is the smallest it's the smallest unit you can have. So that way you can represent Bitcoins in a signed integer. And you also have the timestamp of the transaction finality. So that's when it's finally sort of cemented by the blockchain, when it's cemented into the blockchain. And you also have solutions for the input scripts. Again, I'll go into scripts later, but it's basically a way of proving that you can spend the money in that input, say by showing that you own the private key to the address that the input was sent to. So nodes distribute and store the blockchain among each other, and nodes will accept a blockchain if it's longer than the current one, but I went into that. So scripting is a rather interesting part of Bitcoin that I'd be surprised if people knew about, because it's not very well known. So when you actually send Bitcoin to somebody, you don't send it to an address as you might sort of think, or as sort of wallet software abstracts it to. It's actually every Bitcoin transaction has a bytecode in it that can be executed on a virtual machine. I mean, people often talk about Ethereum, which I'll go into later, as being sort of a virtual machine that can run smart contracts. Well, actually, Bitcoin supports smart contracts. It has an entire virtual machine inside of it that can run stack-based scripts, which is a bytecode. You can see sort of, I got a example script here for a basic transaction. It's stack-based, so if you've used a stack-based bytecode before, you should be able to recognize it. But essentially, first you push the signature onto the stack, then the public key, and then this is a duplicate instruction, hash 160 bytes, hash of recipient's public key, verifies it and checks the signature. So I'm not going to go too in depth on that, but it basically checks that the person that you sent it to has the required private key for the public key address. You put in the public key address you want to send it to, and then they put in their they sign it and put that there, and that way you can verify that they own the private key. And this opens the ability to have a full virtual machine, basically adds a lot of possibilities. So for example, you could have like a time-based transaction where the transaction will only be spendable after a certain amount of time. So you could have like a deposit where you send the transaction, but you'll only be able to get it back after like a week or something. You could have multi-key receivers. So you could have a transaction where multiple people would have to sign it in order to receive the money. So sort of an escrow service. Or you could have stenography, where you could sort of hide data inside of the bytecode, perhaps, which people might not see, because most people, when they're looking at a Bitcoin transaction, look at it on sort of a website which abstracted away and just shows the to address and the from address and the amount. It might not show the sort of hidden data inside the bytecode. There's one interesting use, which is sort of distributed hash cracking. You could send a transaction which requires a hash to be cracked. It requires somebody, if somebody cracks a hash, only then could they then spend the Bitcoin. And there is actually one transaction that somebody sent that allows this. If somebody found a collision between a collision for a hash, they would then be able to spend the Bitcoin. So sort of providing rewards for people performing computation in a way. And you could even have sort of multi-chain transactions. That's where transactions happen between multiple sort of blockchains with oracles, because you could have, say, the public key of a known oracle. Say you know some guy who you both trust, and he has a private key and you have his public key. You could have a transaction which requires him to verify it, and he would only you trust him to only verify it upon certain conditions. Say, if it's a bet, he only verifies it if a certain team wins the football, for example. So lots of interesting things like this. And this is a link to a compiler for Bitcoin bytecode, if you're interested in that. It's called Miniscript. So transaction fees, so the total amount of inputs does not have to equal the total amounts of outputs in a transaction. So any remaining amount of coins will go to the person who mines the transaction. So when a miner submits a block to the blockchain, they can specify an address which all of the spare coins will be sent to. If they don't specify any address, or they specify the wrong address, then the fees will be completely lost, and that's happened a couple of times. And since the miner can only have so many transactions in a block, they prioritize transactions that have a higher fee, because as I said, Bitcoin has about a 2 to 4 megabyte block size limit. So that's why having a higher fee on your transaction will potentially have your transaction be included in a block faster. And larger transactions obviously use more space in megabytes. So nodes that are mining blocks will probably not want to include your transaction unless it has a high fee to compensate for that lost space. So Bitcoin transactions are theoretically immutable once they've been added to the blockchain. Theoretically, they can't then be modified unless somebody was able to produce a longer blockchain. So as I said before, to change something, to change a block in the blockchain, every single following hash would have to be recalculated, and you'd have to recalculate the proof of work of the first block, of the block you're changing. So that's why we have something called confirmations. Every block added after your block is known as a confirmation. So normally most people will be fine once there's sort of 6 confirmations. Having 6 confirmations, as in 6 blocks added after the block that contains your transaction, would require 10% of the entire computing power currently on the Bitcoin network in order to modify that transaction. So it's quite unlikely to happen. And as more blocks are added, it gets exponentially harder to modify it. So mining. So all of the nodes on the Bitcoin network want to gain rewards from mining blocks. And they do that by, as I said, changing the nonce value until it's lower than the target number, until the hash of the block is lower than the target number, that should say, actually. So on average, a node cracks the hash of the block and every 10 minutes and is able to add a new block to the blockchain. So about every 10 minutes, a new batch of transactions will be added to the blockchain. But that changes. It could theoretically, a node could, the first try, it tries a random nonce, it gets the hash and it's under the target, and they could add something to the blockchain instantly. And that happens every now and then. And also every now and then, all the nodes get really unlucky, and it takes 30 minutes to find a nonce value that fits the required range, and it takes a while for a new block to be added. So there's a bit of randomness there. And every 216 blocks, which would be two weeks if the 10-minute sort of average or target was kept, the network recalculates the task to compensate for more or less computing power being on the network, because obviously as time goes on, computers get more powerful, more people start mining, maybe electricity costs go down, something like that. Sort of factors affect how much power is on the network. So if too much power got on the network, then theoretically the delay would go down a lot as people were able to calculate hashes faster. So the network recalculates the target. So it could, for example, make the target number lower, and that would again decrease the range that the hash would have to be in, make it harder for nodes to find a block that they could add to the blockchain. And every time a node successfully mines a block, it gets a reward. The reward at the start of the network was 50 Bitcoins. That's quite a lot, obviously. It wasn't back then, though. Every 216 blocks, so 4 years if the average is met, the network completely halves the reward. So currently it's on 6.25 Bitcoin per block mined. That's still quite a lot. And that happened in May 2020, and you may have noticed, if you're keeping up with Bitcoin prices, actually the reward drops. Bitcoin becomes more scarce because less miners are earning money. And eventually it will halve until it's a negligible amount. And at that point, about 21 million Bitcoin will be in circulation. So we'll reach about 21 million Bitcoin, and that will be the final cap. No more will be produced. And when the block reward is 0, you may think, well, there'll be no incentive to mine transactions, but the fees will still be there. Nodes will still earn money from fees being added. Those fees will become even more valuable because the currency will get more scarce. So the reward will likely be about the same, and I don't think you get a huge decrease in nodes sort of mining. So Monero is another interesting cryptocurrency. It came a bit after Bitcoin, and the ledger is obfuscated. So in Monero, you can prove a transaction is valid without knowing who it's to, who it's from, or how much money is even being transacted, which is quite incredible, because I can sort of prove to you that I've sent you sort of 5 Monero, and I can prove to other people that I sent you that money, but they don't know who you are, who I am, how much I sent you, but they know that I had enough money to send you that money, which is a bit confusing, but it works. So each account has a private view key, which is essentially an address that allows you to see incoming transactions. So you could even give that private view key to, say, like an accounting software, and it will be able to see your incoming transactions and sort of make use of that without being able to send transactions, because you need the send key to send transactions, which is another private key. And then finally, you have the public address. So stealth addresses are a way that Monero obfuscates transactions. If I will send you money, or Monero, I generate a random address for you known as a stealth address, and I send the money to that address in block to the blockchain, saying sort of, I've sent this money to this stealth address, and the receiver looks through every block that has been published and can use the view key to decode it. And if it successfully decodes, they will be able to see the stealth address and the private key, and they will then be able to spend that money. And they will note that and keep track of that, so they know which stealth addresses they own. So it also has ring signatures, which is a way you can have sort of, say you can generate 50 private keys, and I can cryptographically prove that a message has been signed by one of those private keys without actually knowing which of the 50 signed it, which has a lot of sort of uses. For example, one common example is you could say sort of give everybody in government a private key, and then if there was if somebody in government wanted to leak something to the paper, they could sign it with their private key, but so you would be able to verify that it was leaked by somebody in the government, but you wouldn't be able to know who leaked it. So that's used in Monero by sort of signing a transaction with a stealth address. So I could say sign a transaction with a stealth address, but you wouldn't actually know that it was me who signed it, because it could be that there were 50 other private keys owned by different people, and you're unable to prove that it was my private key that signed it. So it gets a bit complicated, and I'm not very good at maths or cryptography, so I'm not able to go into too much detail about it. But you can search it up if you want more info. And it also has zero knowledge proofs, which they have a system called Bulletproofs Plus, which is their sort of implementation of zero knowledge proofs. Here's a blog post they did about it if you want to look at it. And this is how they prove that a transaction is valid without actually knowing the amount in it. So as I said, you can prove that the money I sent somebody I had enough money to send that money, but you don't even know how much money I have or how much money I sent. And mining works like Bitcoin, it's proof of work. However, they use a different proof of work algorithm, Bitcoin SHA-256. And it's designed to run well on CPUs, but not have a particular benefit on ASICs. If you don't know what ASICs are, they're basically dedicated hardware to just calculating hashes. They're really good at calculating hashes for moderately low power consumption, and quite good speed. And they're typically used to mine Bitcoin instead of using a GPU or a CPU. But the problem with those is that they require lots of money. So it basically makes the network filled with miners that have a lot of money. And I couldn't just set up my computer to mine Bitcoin because my computer isn't as powerful as these ASICs, and it just wouldn't be able to compete. So Monero is designed that it can be mined on just any one CPU without giving particular benefit to people that can afford ASICs. Every 2 minutes, a new block will be minted on average. That's the target. There's no maximum block size, unlike Bitcoin, which has 24 megabytes, and it also has infinite supply. So as I said, with Bitcoin, this Bitcoin supply continues to halve. Moneros will just constantly mint at the same rate. That's because they don't believe that there will be an incentive to mine once the rewards get to zero. And mining is critical to the network. If people don't mine on the network, it becomes insecure. So they have infinite supply, and by May 2020, 18 million coins have been minted. But after May 2020, they've changed it, so 0.6 XMR will be released every block. So that's quite a bit less than Bitcoin's, but obviously the block rate is much faster, so it's much easier to create blocks. So Ethereum is another blockchain. It went live in 2015, and it uses proof of work as well, and which is where you sort of calculate the hashes. And it includes the Ethereum virtual machine. So on Ethereum, an address can either be an account, or it can be a contract. So a contract is basically just an address that has associated with it Ethereum virtual machine bytecode, and also a set of persistent data storage that it can access atomically. Any address can call a method in a contract, but it must pay gas, and gas is essentially like the fees of it's just fees. It's another unit for naming fees. So each bytecode instruction has a gas cost associated with it, just a fixed number. So complicated instructions will have a higher gas cost, and easier instructions will have a lower gas cost. So it should sort of even out, so that if you want to run a very complicated smart contract, you'll have to pay a high fee, because obviously that will use more execution time on the nodes running it, and it will use more memory space or whatever. So when triggering the method, you'd specify the gas limits. That's the maximum amount of gas you want to spend, because it's not always going to be equal, because there's sort of control flow, there's sort of if statements. So you specify a maximum amount that can be spent, and you also specify the amount of ETH you want to pay per unit of gas. So if you pay a higher gas cost, that essentially means you're paying higher fees, and that will make your method call more desirable to be ran by a node running the Ethereum virtual machine, similar to sort of including a very expensive fee in a Bitcoin transaction. So Ethereum 2.0 is they're changing Ethereum to be proof of stake. It's a gradual change. It's not fully developed yet, but the network is live, and you can use Ethereum 2.0. And it uses proof of stake, which is basically, instead of having people calculate hashes to prove the validity of transactions, you instead have validators which confirm transactions, but they don't confirm it by sort of calculating a really long hash. They just say this transaction is valid. I bet you sort of 32 Ethereum, or not Ethereum, ETH, that the transaction is valid. And if it is correct, I will earn a bit more ETH. And if it's incorrect, that ETH will be sort of taken from me by the network as a sort of as a fee to encourage people to correctly validate. So you do have to have a minimum of 32 Ethereum. Sorry, not Ethereum, ETH. I'll go into the difference between Ethereum and ETH later, to do staking, which is why you have staking pools, which is where a group of people will all put their ETH together to make up the 32 ETH, and then they'll be able to stake. So there's a problem with this method, because it does require you to have quite a large amount of ETH. I mean, 32 ETH is quite a lot. I mean, ETH is at least sort of $1,000, I think. I think it's 2,000 something. So it's very expensive. So that is a drawback with it. It rewards the richest and prevents sort of a way of monitoring sort of the consensus, because people with more Ethereum will have a higher say in how the network is run, which is fair enough. So ETH is actually the native token of Ethereum, the blockchain. So when you see people saying, I'm going to buy Ethereum, normally they're actually talking about Ether or ETH, which is the token, as opposed to the blockchain. So that's just a small sort of difference. And that's what you use to pay gas. All gas has to go through ETH. So I'll go into, I've not gone through all cryptocurrencies. I've just gone through three, because we don't really have enough time. But there are lots of other interesting ones. I'll leave some links at the end. Why would you want to use cryptocurrencies? Well, they're trustless. So actually, let me just reload this. Yeah. They're trustless, so you know that the bank. How do you know that a bank actually has your money? So if you go on, you have a certain amount of money, but you have no way of verifying that. The only, in fact, they don't have that money because they invest it, and you have no way of verifying what they've invested into, and you have no way of knowing their actual amount of liquidity. I mean, that will be they're decentralized, so there's no chance that the government can, there's no chance that anybody can deny you service from using a cryptocurrency. Unlike banks, because the bank or the government could at any time deny you service from your money. If, for example, there were tax reasons or anti-money laundering reasons or anything like that. And there are examples with this. For example, a lot of banks don't allow you to deposit any money which comes from a cryptocurrency exchange. So they essentially block you from selling your crypto. And adult websites have been denied service from Visa and MasterCard. So there's a risk that your business could be completely disrupted by just the government or a bank refusing you access, which can't happen with cryptocurrencies. And also there's always the risk that the government can just print your money, which of course they're doing right now. But with cryptocurrencies, the network agrees on what money is minted. So you're free from regulations. It's global. There's no sort of restrictions on who you can send money to. You can send money abroad just fine. It's irreversible. There's no chargebacks that you have to worry about. And it's greater anonymity, because Bitcoin's pseudo-anonymous. So I don't know which person owns an address, and there's better security. I don't have to trust that the bank isn't going to get hacked. I don't have to worry about the fact that they're using insecure text-based two-factor authentication, stuff like this. I manage my private key however I want, and I can ensure that it's safe. So if you want to use cryptocurrencies, say Bitcoin, I recommend Coinbin is a good tool. It's an offline website. So it's a website, but you can download it and run it on an air-gapped machine, for example. And it allows you to, I've got it here, it allows you to create new addresses, to verify them and to sign them, and to broadcast transactions to the network. So you can do this all in just JavaScript, and you can sort of do the whole process of sending money yourself. There's also Electrum. If you're actually going to use Bitcoin, I do recommend Electrum. It's a software wallet. It's quite popular. I would say do your own research on which sort of software to use, because obviously people have lost their money through this, as we talked about earlier. So Electrum is a very good wallet. And it can manage multiple keys, multiple addresses for you at the same time. It can manage sending and receiving Bitcoin very well. So I recommend you look at that. And it has clients for Linux and Mac OS and everything. Electrum I've done Electrum, and BlockCypher is an online tool which lets you look at the blockchain. So if you go to BlockCypher, you can examine blocks that have recently been confirmed. You can look at them. You can look at the transaction amounts. You can look at the fees. You can look at who sent and spent Bitcoin. You can look up any address and see its balance, for example. So that's all you really need to know. I mean, if you download Electrum, it's quite simple to use Bitcoin. There's not too much to know. Monero is a bit more complicated if you want to use it. The Bitcoin ledger is public, but so you can see if I send you money, you can see my balance, and you can see you can see every other transaction that I do, but you would have no way of knowing that it's me that sent you the money unless I told you, for example. Monero actually has a website where they offer official Monero clients. This is probably the best place to get a Monero client if you want it, because it's from the developers of Monero, and they have a GUI and a CLI application that you can use. And if you want to use Ethereum, I recommend MetaMask is the most popular wallet. It's here. It's like an extension in your browser or on your phone, and you can send and receive Ethereum, and you can manage altcoins and other tokens on the Ethereum blockchain. I have it here in my browser. And if you want to use Ethereum, there are some very interesting projects on Ethereum that I've not had enough time to go over really, but I'll just put them here. Uniswap is a decentralized exchange. So it's an exchange that runs completely on smart contracts, on public code, on cryptography. So you can sell and buy Ethereum tokens without going through any central entity like an exchange. So I really recommend this. It's a great tool. And you also have Aave, which is decentralized borrowing and lending. So you can see here on Aave, there are lots of different assets which you can borrow or lend for different yields. So I could say, give my money into an Aave lending pool and receive 2% annual yield, which is quite good at the moment, to be honest. So it's very good. And then just to put some of the cryptocurrencies here, just if you're interested, these few that I really like. One is DAI. So DAI is a stable coin, which means it always keeps its value of $1, about $1, as long as nothing wrong happens in the algorithm. And it's completely decentralized. So it works by underneath, when you buy a DAI for say $1, the algorithm will then use that $1 to buy lots of different assets and spread the risk, so that even if some assets go up and down, overall it regains its about value of $1. So it's very clever, and it's an Ethereum token, so you can buy and sell it on the Ethereum blockchain. And finally, Nano. Nano.org is another currency that I really like, because it's got zero fees, so you can send and receive money for without fees, and the transaction times are under. Okay, so Nano is a currency in which there's no fees, zero fees, and it takes under 0.3 seconds for a transaction to confirm, unlike Bitcoin, which can take 10 minutes even if you pay the highest possible fees. So it's a very interesting coin. But as always, do your own research on any of these coins, and I'm not recommending buying or selling or anything. It's just about the technology, this particularly. So yeah, that's everything. So I hope you enjoyed it. And if you have any questions, I'm happy to answer.